All right. See if I can find my. Oh, here it is. So I think I have everybody's missions. Who's going to turn them in, which is good. Now is your last chance for not late. Past this point, 50% late. Clear? Okay, good. So I have a question. How many of you run? All right. My second question. When you're running, is anyone chasing you?
Not usually.
Not usually. Here's something to think about. This is Proverbs 28:1. The wicked flee when no one is pursuing, but the righteous are bold as a lion. Something to think about. Something to think about. I'll begin with a word of prayer. So. That's a joke. Dear Lord Jesus, we thank you for this day. I thank you for the students. Just ask you to bless our work today. Help us to just review for the test this Wednesday. And we just use this time for your glory, Lord. In your name I pray, Lord Jesus. Amen. All right, so your exciting top hat code is over there. Somewhere in here I have an attendance sheet I should hand around. There you go. Like so. So, let's look at the solution here to the mission that you guys have finished, for the most part. Let's see here. So problem one is not especially exciting. I hope you guys got this one. I hope that if I was to give you these questions on the test, you would dispatch them with ease. You know, like these problems should be like taking candy from a baby. To be clear, the baby is sleeping. Yes?
So you're all right if we use negative in angles?
Negative in angles is permissible, sure. I would count this right, whether you put minus 90 or if you put 270, or if you want to be weird and add another 360 to that, I would still take it, you know. Other questions? Let's see here. So I would say there's an ambiguity in certain questions because I asked you guys for the direction. And in my solution here, you're going to see I found standard angle. But I will count it correct if you just found the unit vector in the direction, because I was ambiguous on this point, willfully so. See, because when we talk about the direction of a two-dimensional vector, we could either use the standard angle or a unit vector in that direction. That's true. All right, let's move on here. Key thing to notice here is that when you're over here in like quadrants, 2 or 3, you can't just use inverse tangent. You have to adjust appropriately, right? Either subtracting or adding to 180 degrees. If you just use the reference angle, use the positive ratio of the y and the x component of the vector. All right. Next here, I tried to draw my first picture there. I was like, I don't like that. So I tried it again down here. Basically, we have A at 30 degrees, and then B is at 225 degrees, but we're subtracting B, so opposite. To get to opposite, I add 180 or subtract 180. I decided to subtract, and so that gave me 45 degrees. Minus B is at 45 degrees, which looks something like that. And then, of course, this picture is just kind of a rough guide. To actually find the vector, I broke it down into components, and then subtracted them actually, right? And that got me this, which then gleefully is in quadrant 1, where I can just mindlessly use the inverse tangent to find the standard angle, right? Any questions? Okay, just jump in if you got questions. Problem 3, are you guys allowed a 3x5 inch card with formulas for the test? Oh, why did I do that? Fine, I guess I can't undo it. So yes, that's true. 3 inches by 5 inches. The units were clear. People in the back. You know who you are. And yeah. So not 3 feet by 5 feet. We're 3 inches by 5 inches. You may write on at most 2 sides.
So we can use 2 sides?
You can use 2 sides of the 3 inch by 5 inch card. You may not use 3 or 4 sides of the 3" by 5" card. Oh, this has been done in physics before. I had a person take a 3 by 5 card and tear it along the ply to make it into 2. It's been done. So, yeah. That's why I say only 2 sides. I'll be generous. You can also write on the edge. A cross B. So A dot B should be a number, right? If your dot product is a vector, not good. Cross product, on the other hand, is a vector. It should be a vector which is what? Perpendicular to both A and B. So we should be able to check. We should check it, right? The dot product of this with A and B ought to be 0. If it's not, you didn't do it right. So check it out. Like 2 times 15 is 30, plus 0, minus 30, 30 minus 30, 0. Yay, that's what we like to see. All right, so check the dot products with your cross product. Double check your cross product. There is a like 50% chance you calculated the cross product wrong because you're starting, well, I mean, maybe you had calculus 3, maybe you've already learned how to incorrectly calculate the cross product, so you need to fix that. But I don't know. Do check your work here. So many people foolishly throw away points on this. There's no need. To find the angle, you really have 2 options. Of course, you could use the, there's a formula for cross product with the magnitude of the cross product and the sign, right? But that's really not a very convenient formula because cross products are a pain. The go-to formula is the dot product formula. To find the angle between 2 vectors, I always take the inverse cosine of the dot product of A and B divided by the magnitude of A and B, which in this case is 8 and the square root of 18 and 41, I guess, which I got 69.73 degrees. Now, to find a vector of length 7 perpendicular to both A and B, what I did was I thought, oh, I want a vector in the direction of the cross product, right? So a simple way to make a vector of length 7 is simply to find the unit vector in the direction of the cross product and just multiply by 7. That gives me a vector of length 7, right? That's what I want. Yes?
Do you lose points if you don't put our answer in the nasty decimals?
Do you lose points if you don't put your answer in the nasty decimals? Only if you're a math major. No. No, I do want answers in decimals. Like, will I give partial credit if you didn't here? Well, yeah, but I probably might not. I mean, I might not even take off points for this mission on that issue, but I do actually want answers. If there's a question like this on the test, I would actually like to see like decimals. Yeah. That brings us to another issue, which is you do need a calculator for the test, right? And not one on your dumb phone, right? You need one on like a standalone calculator, which is not connected to the Google. Let's see here. So to calculate the volume of a parallel pipehead, what you want to do is look at the triple product. So that's the dot product of the cross product with C. So it could be plus or minus, right? Because like, depending on whether the vectors are properly oriented or not, you could get plus or minus the volume. So anyway, I just took the dot product of the C, which I don't know the alpha of, with the given cross product I already calculated. That gave me this equation, which gave me alpha is minus 7 over 15, which the ugly decimal numbers right there. So sorry. Is this going to be a problem, the ugly decimals? No? Okay. Problem 4 is not hard. It just looks hard, but it's not hard. So to calculate the length, the squared length of D, we just take the dot product of D with D, which is A plus B plus C. Foil it out, basically. Distributive property gives you these 9 products, but 6 of them are 0 because we're given that the angle between A and B and B and C and so forth are 90 degrees, which means the dot product is 0. And all that's left is the A dot A, the B dot B, the C dot C, which is respectively A squared plus B squared plus C squared. So there's that one. Here, this problem is tailor-made to use the orthogonal and the parallel projection. So the projection of A of B gives you the part of B which is parallel to A in the direction of A, part of B that's parallel to A. And orth is by construction the piece which is perpendicular to the projection. So I identify this as being my C and that being my D, and I calculate it according to the formulas that I told you guys about down here. Basically, it's just take the dot product with a hat and multiply by a hat. But there's a sneaky formula. If you don't want to do a hat, you can do b dot a over a dot a times a. Anyway, I get that. Ugly decimals again, my apologies. And then if I take b minus the projection, I get this, again, ugly decimals, my apologies. And if you add these, you will get back b. And you can check that c dot d is 0, so that's the answer. So if I'm looking to find a part of one vector in the direction of another, projection is the tool I want to use. All right, that's what that's for. The token ninja problem. So 40 steps that way, 80 steps that way, 50 steps that way. And then here's a picture of like the beginning and the ending in the vertical. So like 20 steps up a tree, because of course you're going to walk up a tree. I mean, why not? And anyway, so the distance down, goodness gracious, the distance from where the ninja is to the original point is the length of this displacement vector. Now, if you think about it, if I take this displacement plus that displacement plus that displacement plus that displacement plus that displacement, that would get me where? Back where I started, right? So that makes d just the negative of the other ones. And then to figure those out, again, I just use trigonometry, right? So like delta R1, you know, I've got my 45 degrees. Cosine sine 45 gives me that. My R2, 120 degrees is my standard angle, so 80 times that gives me that displacement. The third displacement's easier. I don't need trigonometry for that. That's just 0 minus 50, 0, right? Don't you love like parallel and perpendicular stuff? It's like finally something down to think about. And then this vertical one is just 0, 0, 20. So anyway, that's what I do. One step at a time, use trigonometry to break into components, and then we add components together. So that gives me a net displacement of that in terms of steps, right? And so the angle, we're just focusing on the x and the y components, I get minus 76.16 degrees, or that if you like, counterclockwise of east. And if you look at the picture I had with the tree upstairs, that help you understand why I took the inverse sine of 20 over this. The magnitude of d is 52.91 steps, so that's what I got. So, yep.
Professor,
Yeah, sure.
solutions to the missions are posted.
Not yet, but they will be. Like after class, I'll do that next.
Thank you.
This one here is kind of a foreshadowing of things to come. We do a lot more of this after test 1, all right? So like, I've drawn some token free body diagrams in here, right? Like balancing forces on a mass. So it's a useful concept even now for like the elevator problem, for instance. But the lion's share of our focus has not been on that. So, you know, there's a lot more about free body diagrams on test 2, all right? That's what I'm trying to say. But this is kind of a precursor to that. So this point right here, if it's in moving, you can think about the mass of that point, and the sum of the forces on that should be 0. So the one force is the tension force down, the tension force up, the other tension force to the left. So you got your T1, T2, T3. The vector sum of those must be 0 since the acceleration is 0 for that point. But I can break down T1, T2, and T3 in terms of the angles which are given, you see? So like T1x is minus T1 cosine theta 1, and T2x is T2 cosine theta 2. The reason for the minus here is because T1 points to the left, whereas the plus here because T2 points to the right. Both of the vertical vertical components of these tension forces is upward, so they get positive both. On the other hand, T3 has a negative component down. So anyway, long story short, we have the x component and the y component of the tensions summing to 0, which gives me this equation and that equation, which I can solve because it's 2 equations and 2 unknowns, the unknowns being tension 1, tension 2. The angles are given here. So I solve the first one for T1, and then I plug it into the second equation for T2, and then I do this thing called algebra. And it tells me that T2 is actually this, which I solved, and I got 0.7771 M1G, and then T1 is 0.6293 M1G is what I calculated. So, yep. Again, my apologies, ugly decimals all around. Violet is not acknowledging me now. I like it. It's very good. So this one here, so here we have a projectile is fired at such a way that the horizontal range is equal to 4 times the maximum height. What angle of inclination was the projectile fired? So here's a picture. We got the range, we got the height. We're given that the range is 4 times the height, but you remember that the formula for the range is 2v0 squared sine theta cosine theta over g. Now you may be like, hey, hold on a second, flag on the play. That wasn't the formula. What's the formula we had? What did I do? Yeah, sine 2 theta. So remember, this is what we had before we made a trigonometric simplification to the formula, right? When we were deriving the formula, we found this first. And this is actually much more convenient for this problem to keep the formula like this. See, because then you can do this thing called cancel the sign with the square over there, right? And if you do that, then that gives us like a tangent, I think. So we get tangent theta is a half, which gives me about 26.57 degrees. So, yep. So does that mean I need to know like trigonometric identities for physics? Yeah, it does. You do need to know trigonometric identities for physics. I do assume you know these things. Yep.
I thought the height equation that you have, or I did the range equation was v naught squared sine squared theta over 2g.
Uh-oh. 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 Oh, man.
Is that correct?
I tried to check these with one of you. I think you're right. I think it's supposed to be 2g there, which means this is what? Incorrect. So there should have been a 2 right here, right? Which would have made... Oh, that would put a 2 on both sides, wouldn't it? So the answer should have been 45 degrees. Very good. This is wonderful. I love it when I am wrong and you are right. That is optimal. Nothing makes me happier. Trust me. So apparently I need to fix this before I post the solution, right? All right, I'll do that. My apologies. I think that 2 is missing from my notes. Oh no, the square is missing from the notes. Beware of the height formula in the notes. There's a typo there at the moment. So we did derive it in class, and I think what we derived in class was correct, right? All right, problem 9. So you shoot an arrow, speed v0, angle 30 degrees. The arrow leaves the bow, height 2 meters. You're trying to shoot a cat. Of course, tree 200 meters away, in a branch 22 meters above the ground. So find the speed v0 in order to shoot the cat. Now, so some of you may have just put like h equal to 20 and solve for v0. This would be wrong because that completely ignores the horizontal, and it won't actually give you an x of 200 meters when you reach the zenith of the flight. If you investigate it, you'll have about 70 meters, right? So you have to solve both the x equation and the y equation at once. So the x equation is v0 cosine theta 30 degrees times time, and which gives us about that, 0.866 v0 times t, and the y equation. And listen, I put the origin here. You could put the origin where the motion starts. It's up to you. We should agree on the answer because like if you put the origin up here, your final position's not going to be 22 like me. You're going to have 20, right? So anyway, these are the 2 equations which govern the motion. And then we got to think about the time we're interested in. We're interested in the time when we, finally get the cat. And that's when 200 meters is this and 22 meters is that. So I've got myself 2 equations, 2 unknowns. What I do is I take the first equation, solve for t, which gives me this. I don't know v0. And then I plug that into the second equation. And something relatively nice happens. The algebra is this. So the v0's, they're canceling here. That leaves me a v0 squared over here. And you can clean this up like so, and then solve for v0. And lo and behold, you get that, which then gives you 52.32 meters per second. The time it took actually is about 4.414 for what it's worth. Mostly putting that there so that the grader has an easier time of checking your work, whether or not you're like half correct or totally incorrect. There's different ways of being wrong. But hopefully you're right. Hopefully you guys got this. I guess I could say show of hands. All right, fine, show of hands, who got 52.32 meters per second. All right, there's hope. Hooray, hooray. Ah, yes, one of my favorite questions. So you got this dude, he throws a sandwich at 15 meters per second, like so. It goes 10 meters, like that. And then the question is, at what theta was it thrown? All right. So the last one is a lot like this question, but it's a little bit different, right? So the last question, I fixed the theta and I made the velocity variable. This one, we've done what? We've fixed the velocity, we've made the theta variable. Those are two different variations of basically the same problem because they're both solved the same way, which is that this is projectile motion, so you set up the kinetic equations and then you solve them. This one, if we solve for the x equation equal to 10, and we plug that, which gives us 10 over 15 cosine theta, we plug that into the y equation, that gives us this right here, like so, which then gives us a tangent for this guy and a secant squared for that. But I know that secant squared is, tangent squared plus 1, which when I plug that in there, then I've got a quadratic equation in tangent theta. In quadratic equations, we can solve. So we solve it, and we either get tangent theta is 4.47 or 0.1209, which then, after inverse tangenting those, we get 77.39 or 6.897. It's interesting. So we kind of expect two solutions because you guys remember, like if it's like level playing field, if you get a particular range from like 30 degrees, you'll get the same thing from like 40, so it's 15 less than 45 degrees, like 15 more than 45 degrees is 60. So like 30 degrees and 60 degrees will give you the same range if you're beginning and ending at the same height. That symmetry is spoiled here because we're not beginning and ending at the same height, but we still kind of expect there's two solutions. There's like a faster time solution to that range, and there's like a slower time solution to that range, but we do expect two solutions. It makes sense that there's two. But they're not symmetric about 45 degrees because this is not a, same height beginning and ending projectile problem. All right, this one here, we've got cannon, we shoot it, the ball lands 1,000 meters away, it blows up, we hear the sound 7 seconds later. Then the question is, what speed and angle of inclination did we shoot the cannon? So first order of business is to figure out what time the ball actually landed on the ground, right? So if you think about it, we're traveling 333 meters per second back 1,000 meters, right? How long does that take? Well, that takes 3 seconds, right? So if there's 7 seconds till you heard it, that means the explosion actually happened when 7 minus 3, 4 seconds, right? It was 4 seconds when the boom happened. And then we're back to the same thing again. X equals V naught cosine t, y equals this, right? And we know that at 4 seconds, it gets there, right? So 4 seconds we have, and we also have x equals to 1,000 and y equals to 0 at 4 seconds. So we can plug that into our equations, and we've got, this, that. We do algebra and eliminate. Let's see what I do. I solved for V naught this one, and then I plugged it into the other equation, I believe, which then just gave me a tangent again, and then I solved for theta, and I got 4.483. Yep.
Would it be acceptable to use the range equation in this scenario since it
Yes, I think so. Yep. So I could have used the range equation here. Did you get the same answer? Cool. Good. Yeah, I probably could have used the range equation here and made my life easier if I wanted to. Okay, so ninja on horseback problem. There's two ways to interpret this. The one way is that you're, galloping towards the target and throwing the knife, right? The other is that you're galloping away from the target and throwing the knife behind you. Either solution, if you have either one of those, I'll count it full credit. Okay, I didn't require you to have both solutions, but I think the wording doesn't You could go either way, you know. At least one of you said you could go either way. So if that's how you feel, I wanted to value your opinion. So I have. So I put both solutions. So if you're galloping towards the thing and you're at what was it? I've lost it. How fast was the horse galloping? Oh, 15 meters per second. So the horse is galloping 15 meters per second. You can throw it from 20 meters per second. So relative to the earth, you're throwing it 35 meters per second. In that scenario, velocities add. So that's why I have this 35t. On the other hand, it's dropping 1.25 meters. So I just decided to put the origin like here-ish. I meant to erase that. I'm sorry, guys. Anyway, so 1.25 minus 1/2 gt squared. When y equals to 0, it hits the target, which tells me that my time is that, which is 0.5051. And so then I put that into the 35 and I get 17.68. So 17.68 meters if I'm going towards the target. If I'm going away from the target, on the other hand, instead of having 35 meters per second, since I'm going 15 meters per second this way and I'm throwing it 20 meters per second back, the velocities subtract, right? 20 minus 15, I actually only have 5 meters per second towards the target in that scenario. And so my equation is like x equals to 5t and y equals this. Now, and I get 2.526. So there's that's a problem. This one here, we pretty much worked this in class, right? So any question about this? Yeah.
Would you be all right if we were to just recognize that it accelerates for 4 times that and then decelerates at 1 times that, so that it just travels 5 times the length? Or do you want us to show it in more specific amount?
Yeah, I need to see work. Like if you've noticed the pattern and you can just write down the answer, that's lovely. But I actually do need to see like derivations from the kinematic equations. Yeah. Does it have to be exactly this? No, I don't think so. I mean, there might be another way to derive it that I hadn't thought about for sure. But this is how I see it. So like we've got 4 times the weight for the rocket force during the acceleration phase. Now, would I give significant partial credit in that scenario? Yeah, a lot. But so let's see here. So 4 times the weight gives me, like you said, 4 times g as the acceleration. So then there are 2 things, right? You can, the timeless equation over phase 1, the timeless equation over phase 2. Over phase 1, we've got the middle velocity v1 squared equals to the initial velocity v naught squared plus 2 times 4g L, because L is the distance that we're given that it's accelerating over. X is the distance we don't know, the braking distance, and that is related to the final velocity and the middle velocity in this way. But the thing is, we're given that the final velocity and the initial velocity are both 0 because it begins and ends at rest, which then gives us just v1 squared equals to that, v1 squared equals to that. We don't care about v1, right? So we just set this equal to that, and it gives us that x is equal to 4L, right? So since x is equal to 4L, that means the total distance is L plus x, which is 5L. 5L is the total distance traveled. So there's that. This one here, problem 14, you've got a boat, and it's got 2 things going on. It's got a wind force on it, and it's got a water force, right? So the water's pushing the boat that way, the wind is pushing the boat that way. The question is, what's the net force? Well, add these 2 vectors, right? It's a vector sum. The force is a vector. You add them, you get 183.90. What's the acceleration? Force is mass times acceleration, right? So the mass is 270. The acceleration, I don't know yet, but I almost know it because all I got to do is take this here vector and divide by 270. And lo and behold, my acceleration is 0.6667, 1.4444 Newton per kilogram, because I forgot to write meters per second squared. My apologies. So like, I wrote newtons here and I was like, wait a minute, no. I was like, oh, divide by kilogram. Now that's just a weird way of writing what? Meters per second squared. So the magnitude of this, the square root of this squared plus that squared, square rooted, is 1.59 meters per second squared. There's the magnitude of my acceleration. So this is what I was talking about. If you give the answer as a unit vector in that direction, cool, fine. That's also a reasonable way of writing the direction. But I was actually fishing, pun slightly intended, 65.22 degrees, because it's pointing in quadrant 1. Man, they keep pointing in quadrant 1. That's so boring. I gotta make them point in quadrant 2 or 3. I learned more from that. Anyway, so there it is. Any questions? Jump in if you have a question. this one here, we have a unit vector directed 30 degrees north of west. So the way that works is this is west. That's the northern direction, so 30 degrees north of west looks like that. And I've got forces F1 and F2. So F2 is pointed in the direction of U hat, like so. F1 has, what was it? Oh, it's given right here, right? So the net force is the sum of these two forces, so I add them. So F1 is just given, right? 3 and 6 newtons respectively. The magnitude of this is 20. The unit vector in the direction of U hat, well, I just found it convenient to think, oh, if it's 30 degrees here, it's 150 like that. So the unit vector is cos 50 sine 150, right? Which gives me minus 0.866.5. That checks, right? It's pointing left and it's pointing up. That's the right kind of direction for that direction. So I multiply that by 20 and I add those vectors. That gives me the net force. The net force is the mass times the acceleration. The mass is given to be 10 kilograms. Don't need a calculator for this one, right? You just divide. And you get minus 1.432 meters per second, 1.6 meters per second squared. The magnitude of this, then, square root of these things squared, is 2.147 meters per second squared. At long last, we have a vector which is not pointing in quadrants 1 or 4. It's pointing in quadrant 2, which means to kind of find the standard angle, I need to take 180 minus the reference angles, minus the angle from the reference triangle. So, 1.6 divided by 1.432, that gives me this angle here. I take 180 minus that angle to get the standard angle, which is 131.8 degrees. Moving on. So this one here, it's a lot of talk, but it's actually really easy. All right. So to find the velocity, so what we're looking at is 3 coordinate systems, right? Possibly inertial, possibly not. And this is the position measured from some particular particle. So this is its position as a function of time with respect to the x, the y, and the z coordinate systems. To find the velocities, we simply differentiate, right? Just differentiate. And so there's the velocities. Great. To find the accelerations, differentiate again. And so the accelerations are similar, right? But then I gave you a hint, right? Which is when we derived, if 2 coordinate systems were inertially related, the magnitude of the accelerations have to be equal, all right? So what that means then is that if x is an inertial coordinate system, which I think was given in the problem statement, right? Then it is true, it is possible, not guaranteed, mind you, but it's possible that y is also an inertial coordinate system. But on the other hand, z cannot be, because the magnitude of a, of the acceleration with respect to the z coordinates is 6t, right? And this has to be an identity for all time, right? It's not enough that they're equal at just like 1/3 of a second. That's not a meaningful thing. Like positions have to be comparable like over a bunch of times, not just one time. So anyway, that's pretty much it. Yep.
Could you explain more so what it means for coordinate systems to be inertially related?
Sure. So 2 coordinate systems are inertially related means that they're related by a rigid motion in the sense of high school. Well, so like R2 is equal to R times R1, all right, plus T times some vector, let's say C, plus B. So I said that's our definition. So like coordinate system, it's a coordinate system 2 and coordinate system 1, these would be inertially related. Now this here has to be a rotation matrix, so it's a rotation matrix. But let me just kind of put it in more sort of common terms. So you guys remember high school geometry? You study whether 2 shapes are congruent, right? So the first idea in an inertial coordinate system is it should recognize congruent objects as being related by some transformation. But it's more than that, because we also want to allow for constant velocity straight line motion as part of our coordinate transformation. So it's kind of like a mixture of the idea of congruence in high school geometry and also just straight line constant velocity motion. Constant velocity motion's this last piece, like TC plus B would just give you like constant velocity of like say R1 equals to 0 in the R2 system. But that's it. But we can't really do much besides say that. I don't think I'd even ask you to write it on the test, for example. What I do want you to know is like what we did in the mission, which is that if the two coordinate systems are inertially related, the critical thing was that the accelerations just have to be related by a rotation matrix. And then from that, we can derive that the magnitude of the accelerations have to be equal. The larger point of why I'm even talking about this, though, is just that it's the context in which Newton's laws make sense, right? Given an inertial frame of reference, if I have another inertial frame of reference, I can meaningfully talk about setting up Newton's laws in both of them in a coherent and like consistent way, consistent fashion. If you wanted to set up equations of motion for physics outside of this context, you need a more general setting. And so some of you guys in mechanical engineering might go on and study what's called Lagrangian mechanics. In Lagrangian mechanics, we can consider general coordinate transformations, which allow for much more things. Like you can use coordinate systems which are curvilinear and things to set up equations in that way. But that is not Physics 231, so I shut up.
Hey, Professor,
Yeah.
wouldn't the magnitudes of AX and AY be 4? Because taking the dot product, wouldn't it be...
Oh, but the dot product of the vector with itself is the square of the magnitude. So you have to take the square root after that. It's easier than that. Just think about it intuitively for a second. What's the length of the vector 0, 0, 2? Right? It's length 2, right?
Yes.
So that's the magnitude. I mean, I guess to say 6t there, I really do need t to be positive, fair enough, right? So, but moving on here. We talked a fair amount about this problem like last class, so I think I'm going to go on. I got minus 1.781 meters per second squared for part A. I got 2.13 for part B and minus G for part C. Yeah, you should worry, obviously. Problem 18. So you're given the acceleration, right? And you're supposed to find the velocity. So like what I would do in this situation is integrate. There's different ways of handling this. Like you could just anti-differentiate, add a constant, and then fit the constant given the data. Like that's one way. I'm just integrating from 0 to t and changing the variable to tau just for the sake of, using that approach. If I do that, that gives me v of t minus v of 0. And the integral of cosine tau and that is just, 1/2 sine 2t tau, 1/2 sine 2 tau, tau squared over 2, and this integrates to 2e to the 2 tau. You got to evaluate from 0 to t, which gives you this, that, and notice the minus 2 here, because e to the 0 is 1, right? Watch out for that. And so then when I add the velocity at time 0 of 1, 2, 2, it gives me this. There you go, that's the velocity at time t. Then to find the position, I integrate again. So integrating dr d tau from 0 to t gives me r of t minus r of 0. Integrate these things with respect to tau, I get this, that, and that respective. Evaluate from 0 to t. Careful, remember that e to the 2 tau integrates e to the 2t from the top, but the bottom bound gives me e to the 0, which will give me that minus 1. Now, thankfully, I made r of 0, 0, so we can just kind of forget about that. And this is straight up r of t once I evaluate, which gave me that. Yep.
For your position vector, how is the y term 2t plus t cubed over 3, even though in the line of it was...
Excuse me. Ooh, I think that is what we call a mistake. So the answer in short is women. Follow man, right? It's all Eve's fault. Go back. Think about it. Wait, were we not to say that? We're not to say that. Should I retract that, Violet? Should I retract that? I should retract it. Okay, fine. I used to be able to say that here. Maybe we've grown. I don't know. So t cubed over 6 is what I should have there. You're absolutely right. Yeah, that should be a 6. That gives me another thing on my list of things to white out and fix before I rescan this and post it. I need to rescan after I make my corrections. So thank you guys. You're helping me correct my solution. That is helpful. I really do appreciate the corrections. When you guys see something, say something. I'm not joking. Like, that's important. So A, acceleration is t times a constant vector. So this kind of thing, the way to do these kind of problems is just to like pull the constant vector out of the integral like this. And you can actually look at it this way. It's really like dv is, you know, t times c dt, integrate both sides. Integrating this gives me vf minus v naught. Integrate the other side like t naught to tf. So I get the constant vector times this thing, which then I solve for v. And then I'm like, oh, okay, well, I'm going to put t equal to tf equal to t and t naught equal to 0. And I get this. Now, maybe you just went straight from here to there and you're like, that's the answer. That's fine. Like, I don't think all of this work has to absolutely be shown. Like, I think it's totally legit to go straight from here to what's boxed. Like, that's what I usually do. I'm showing my work right now to try to make you guys understand what the logic is. But truth be told, I would regularly go straight from here to here, especially if I was a physics student in a physics class. Now, if I anti-differentiate this thing, I get a t v naught from that term. I get a, oh look, I learned how to do the math this time. 1/6 t cubed, see, I learned, times the c vector here, and then plus a constant from the anti-differentiation. Oh, question. What have I done?
For the equation, would you expect that the v0 vector to be v0, like could it be another variable?
I think I said that the velocity at time 0 was given to be v sub naught. So that's why I put that there. Yeah. If I don't say, then it's my own stupid fault. You can put whatever you wanted there in terms of like labeling. But I think at the problem statement I said up here, I said that the initial velocity is v naught vector at time t naught. That's why I have to put that there. Yeah, it's just words. So likewise, here I anti-differentiate for a change. I've been doing a lot of integrating over tau. I thought it would be good to anti-differentiate for a change. So I anti-differentiated. When I anti-differentiate, you have to be careful. Add the constant vector. If I do that, then I can plug in time 0, which will have to give me r naught. That was given, that at our position at time 0 is r sub naught. But that's also 0 times v naught plus 0 times the c vector, which is characteristic of the problem statement, and then plus c2 vector. So apparently c2 vector is just r naught. It's not always that, though. Like that other problem with the exponential would mess that up. You can't always assume that the constant vector you add is just the v naught or just the r naught. If the thing you're integrating actually has an evaluation which is non-trivial at 0, it'll mess it up. So watch out for that. Anyway, here it is for this one. That's the answer. Okay, what else here? Then problem 20, I don't really have much to say about that because it's in the notes. This is example 3.28. To summarize, what we did was we looked at Newton's law, which was ma is equal to the force, the net force, which in this case was minus beta v. And then I separate to dv over v. I integrate both sides. I did the algebra. That was how I found v of t. For part B, we used the standard trick, which is that the acceleration is v dv dx. And then so mass times acceleration is minus beta v. This time the v's cancel, which is kind of weird. And that just ends up giving you like, you know, dv is equal to minus beta over m dx. And again, you integrate. So this is actually the same method that we use to derive the timeless equation, right? And that is something that I might ask you to do on the test, right? Like derive the timeless equation. Can you do it? You should be able to. But anyway, that's pretty much it. I guess I got time for like one question about mastering, but the mastering problems are not irrelevant. A lot of those are pretty decent test questions, right? They're not that hard. They're not that easy. They're kind of in the middle. There's good test questions in there for sure. Yep.
How many questions are there on the test?
How many? Oh, enough. The inevitable, how many questions on the test question. Let's see here. Did I put an old test? I think there's an old test here, right? Now, so here's like the test from like last year, and it's okay, but there is one thing that is a little bit off with respect to this year. Problem 8 wouldn't be relevant. Problem 9 wouldn't be relevant. Like these would not be on your test. because we haven't covered that stuff yet. So I changed the topics just a little bit. Yeah.
Do you have a blank copy of that?
No, but you can print it out and then like cover it up. If you email me, I might send you one. If I can find it. I think I'll find it. Just email me. Oh. Yeah, so usually the last problem is kind of like a bonus question, you know? But anyway. I think that's all I got for you guys today. So I'll see you Wednesday. Yes, sir. How many what?